This time we're going to do an ESD experiment using ferrite cores and see how the cores work versus the number of turns on them. In the Ferrite catalogs, you can see this kind of thing where they plot impedance versus frequency and the number of turns, but we're going to do this in the time domain here using ESD. First, let's look at what's happening here. So we have a ferrite core, and I haven't shown the core here, but there's a core in these turns. But the turns have capacitance between each of them, and also there may be capacitance from beginning to end, especially if they're wound on top of each other. Normally the impedance of this would be a constant times the number of turns squared. So if I double the turns, I get 4 times the impedance. However, at high frequencies, these capacitances come into play, and in addition to that, especially if these loops are big, there could be phase delays around this. For instance, if there's a 180-degree phase delay between the first and along the first and to the second loop, this loop will be out of phase with that one, will cancel it. I think the capacitance probably dominates, but I think this other effect could happen too. So we're proportional to the number of turns squared, except for the stray capacitance and potential phase shift on the turns. So let's look at some data here. I have a Keytech Mini-Zap ESD gun set for 1 kV. And actually I better take this ferrite off. We want it without the ferrite to start with. So here's our current loop back into the probe. The waveform will look a little funny, not quite like IEC because of this arrangement here, but that's okay. So let's go over to the scope, and I'll fire the gun. This is 1 amp per division and 10 nanoseconds per division. Probably should point with this pen, will be better. So here we have a 4 amp rising edge in something like a nanosecond or 2, especially from here to here, it's about a nanosecond. So remember this, we're about not quite 4 amps in something like a nanosecond or 2. Now, I'll just put on the ferrite core. And we'll go back over to the scope. I'm going to fire the gun. Getting better. Let's add a second turn. Much better. That's why we use ferrite core sometimes for ESD problems. It's slowing it down, reducing the amplitude. Let's go to a third turn. We want to make this really work well, right? So let's do a third turn. Making sure the core closes completely. Even a little gap in here will make the whole thing not work. Wonder I have any fingernails left working on these ferrites. I think EMC people probably have terrible fingernails for that reason. Here we go, 3. Getting better. Something funny is beginning to happen here. Let's put a 4th turn on. And this is probably all we're going to fit in here. Just 4 turns. And make sure everything is loose here. Because if you force those 2 halves of the core apart by even a millimeter, it's not going to work at all. And now we'll fire the gun. Ah, look what happened here. We're up to 2 amps here now. So the low frequencies are getting better, but now the high frequencies are getting worse. If I had a long enough wire and put 4, 5, 6, 7 turns, this would get worse and worse and worse until the ferrite's not really doing much good at high frequencies, and it's usually the high frequencies that cause the problem. So basically for ESD, I tend to use 1 or 2 turns. In the frequency domain, come up here and take a peek here, there we go. In the frequency domain, maybe above 200 megahertz, I'd only use 1 pass, and below 100, I could use multiple passes, and then there's a gray zone in between. Many ferrite manufacturers now actually give a frequency plot versus turns, and that's helpful. But here you can see it in the real ESD case. Thanks for watching, and there'll be more of these coming. In fact, I've got one planned to do right after this one involving a capacitor that weighs 40 pounds, and I think you'll enjoy it. Hi, this is Doug Smith in the Boulder Dam Hotel, Boulder City, Nevada, near Hoover Dam and maybe 25 miles from Las Vegas. Just want to talk a little bit about what I'm doing here, and you're probably watching some of my videos here. And What you may not know is I also do training here. I've got a classroom and the lab that we're working in right now, and basically pretty much all areas of engineering, including most of electrical engineering, analog digital design, EMC, ESD. Most of my work is troubleshooting designs, getting them to work right, because the big cost for introduction of equipment is delay, not the testing cost. That can be substantial, but depending on your product, you could be losing $100,000 a day in delaying a product and getting it out. So if the design has some problem, it could be an EMC problem, it could be an operational problem, any number of things. But if it's delaying you getting this thing out, it is a real cash burn, and so that's what I help companies with. In addition, I've also got some experience in things like engine and bearing lubrication, which turned out to benefit one of my customers one time. I was able to fix a problem for them, maybe 10% of what they thought it was going to cost, and thermodynamics and other things. So, need any help on any of those areas of engineering, give me a call, and we'll see what we can do for you. Thanks.